Today's lecture will be an introduction to the mesh current method. The mesh current method is a systematic application of Kirchhoff's voltage law. Recall that the mesh current method is only valid for planar circuits. A planar circuit is one that can be drawn such that none of the branches are overlapping. We use KVL in order to solve these circuits, and remember, you can only have the number of independent simultaneous equations equal to the number of branches minus the quantity, the number of nodes minus 1. A mesh current is the current that exists only in the perimeter of a mesh, and it may not necessarily be a branch current. This is something that sometimes confuses students. To see examples of mesh currents and branch currents, please see Chapter 4 in your textbook. In order to apply the mesh current method, there are 4 steps. The first one is to assign a mesh current to each of the end meshes in the circuit. I typically assign clockwise mesh currents. Then you apply KVL to each of the end meshes and use Ohm's law to express the voltages in terms of the mesh currents. Next, you solve the simultaneous system of equations to get the mesh currents. And finally, you use those mesh currents to find any other branch currents, voltages, or power in the circuit. Similar to the no voltage method, if there are any dependent sources, they create a constraint equation, which we will discuss later. Okay, let's look at a concept question. In the following circuit, all of the light bulbs are identical. Remember, identical means same resistance. Knowing that the intensity of a light bulb is proportional to the power dissipated across it, when the switch is closed, which of the following statements is true? First, let's think about when the switch is open. When the switch is open, I have one mesh, and I have 12 volts in series and 2 light bulbs in series. So when the switch is open, both of these bulbs would have the same voltage and the same power. And it would be 12 squared over R. When the switch is closed, it creates 2 different meshes. I'll have a mesh on the left and a mesh on the right. For the bulb on the left, the voltage is now 12 plus 6, or based upon KVL, 18 volts. So the power for bulb A is now 18 squared over R. For the bulb on the right, I will have a 12 volt drop and a 6 volt rise, so that would also put another 6 volt rise across bulb B. So the power for bulb B is going to be 6 squared over R. Since they all have the same resistance, when the switch closes, bulb B is actually dimmer because 6 squared over R would be less than 18 squared over R, which makes the answer for the concept question letter B. Okay, let's apply the mesh current method in order to find values for the following circuit. The first step is to label the mesh currents. And as I said before, I always label the mesh currents clockwise. So I'll label the top one I1, the bottom left one I2, and the bottom right one I3. And now we're going to write the KVL equation at mesh 1. For mesh 1, the voltage across the 30 ohm resistor is 30 I1, based upon Ohm's law. The voltage across the 90 ohm resistor is going to be 90 times. Since these are mesh currents, what you should notice is that the current through that 90 ohm resistor is a combination of the mesh current I1 and I3. How do I know which one comes first? Well, if I'm in mesh 1, I want to draw the polarity on the resistors to obey the passive sign convention. Therefore, that's going to be positive on the right, negative on the left for the 90 ohm, positive on the right, negative on the left for the 5 ohm, and positive on the left, negative on the right for the 30 ohm. So this becomes plus 90 times I1 minus I3. Plus, for the 5 ohm resistor, it's 5 times I1 minus I2 which equals 0. Similar to making all of the current leaving for the node voltage method, if you make all of the mesh currents clockwise, a good check of your work is that the coefficients on the I1 should be positive if I am on mesh 1. The coefficients on I2 should be positive if I'm on mesh 2, and so on. So now, let's do KVL for mesh 2. Starting with the 80 volt source, that's a voltage rise, so it's going to be negative 80. Then I'll have voltage drops across the 5 ohm and the 26 ohm resistors. So labeling the polarities to obey the passive sign convention in mesh 2 is positive on the left, negative on the right for the 5 ohm, and positive on the top, negative on the bottom for the 26 ohm. So it's negative 80 plus 5 times I2 minus I1 plus 26 times I2 minus I3, and that equals 0. Finally, let's do KVL for mesh 3. KVL for mesh 3, starting with the 26 ohm resistor, is going to be 26 times I3 minus I2 plus 90 times I3 minus I1 plus 8, and since that's an outer branch, it's just I3, and that equals 0. So that's 3 equations. So that's 3 equations and 3 unknowns. So when I solve for I1 is equal to 2 amps. I2 is equal to 5 amps. And I3 is equal to 2.5 amps. So now let's use the mesh currents we found to confirm that this circuit obeys the law of conservation of energy. The first thing I'm going to do is to label the values we found on the circuit. So first, I1 was 2 amps, so I'll put I1 here. I2 was 5 amps, so I'll put the 5 amps here. And I3 was 2.5 amps, I'll put the 2.5 amps here. There's only one source, so we know it must deliver power, but we'll write it down. So we had an 80 volt source that has 5 amps flowing through it, and that must deliver 400 watts. Everything else is a resistor, so they all must absorb power. The 5 ohm resistor. The current through the 5 ohm resistor is a combination of the mesh currents I1 and I2, so that would be 5 minus 2. So the branch current for that 5 ohm resistor is actually 3 amps. So we'll have 3 amps. 3 times 5 is 15 for the voltage. So that gives us 45 watts absorbed. The 30 ohm resistor is an outer branch, so the current through that outer branch is 2 amps. And 2 times 30 gives us a voltage of 60 volts. So the power absorbed for the 30 ohm resistor is 120 watts. The 90 ohm resistor is also a combination of mesh currents to create a branch current. I have 2.5 amps to the right, 2 amps to the left. So that gives me a net 0.5 amps as the branch current. So 0.5 times 90 is 45 volts. So the power absorbed by that resistor is 22.5 watts. The 26 ohm resistor is also a combination of mesh currents. So I have 5 amps going down and 2.5 amps going up. So that gives me a net 2.5 amps. That points down. And 2.5 times 26 is 65, which is the voltage. So the power is 2.5 times 65, or 162.5 watts. And finally, the 8 ohm resistor. It's in an outer branch, so the current is 2.5 amps. 2.5 times 8 is 20 volts. 20 times 2.5 is 50 watts. So now, the power absorbed is 400 watts. The power delivered is 400 watts. So we have shown that this circuit does obey the law of conservation of energy. Okay, let's try one more problem. Now we can tell this one's going to have 3 meshes, but there's also going to be a 4th equation because we have a dependent source. Recall, whenever you have a dependent source, that creates a constraint equation. So first, let's label the meshes. The first one's going to be I1. The second one's going to be I2. And the third one's going to be I3. So let's do KVL at mesh 1. Negative 45 plus 15 I1 plus 30 times I1 minus I2, and that equals 0. KVL at mesh 2. 30 times I2 minus I1. Now next, I could either put 20 I2 or I could put plus V naught, but we'll take care of the V naught with the constraint equation. So I'm going to put plus 20 I2. And since I'm making voltage rises negative, I'm going to have minus 5 V naught equals 0 because I2 goes in at the minus sign on the dependent source. KVL at mesh 3. I'll have now positive 5 V naught because with respect to I3, the dependent voltage source is a voltage drop, plus 10 I3 plus 40 I3, and that equals 0. The constraint equation is a relationship between the mesh currents and the dependent source controlling variable. The controlling variable is V naught. So V naught, which is the voltage across the 20 ohm resistor, is the same as 20 I2. This gives us 4 equations and 4 unknowns. So when we solve, we get the following. I1 is equal to 714 milliamps. I2 is equal to negative 429 milliamps. I3 is equal to 857 milliamps. And V naught is equal to negative 8.57 volts. Okay, let's do the last problem in today's lecture. We're going to find the power associated with the 45 volt source and the dependent source. We'll do the 45 volt source first. So the power for the 45 volt source is going to be 45 times the current through that source, which is 0.714, which is equal to 32 watts. Since the current flows from the negative to the positive, it's going to be delivered. Now we'll find the power for the dependent source. The voltage for the dependent source is going to be 5 V naught. So that's going to be 5 times negative 8.57. And since this is a branch current and it's a combination of I2 and I3, the current is actually going to be the sum of the 857 milliamps and the 429 milliamps. The reason it's the sum of those two is because I2 is a negative number, which means that current is actually flowing counterclockwise. So that's going to be 0.857 plus 0.429, which yields negative 55.3 watts. Or another way of stating the current for the dependent source is 55.3 watts delivered. This concludes today's lecture on the mesh current method.